In this video, I'm going to be reviewing how to do mass-mass stoichiometry problems, i.e. where you're given the mass of one compound in a balanced reaction and it asks you to find the mass of another compound from the balanced reaction. This is a very, very common type of problem in AP chemistry, one that we will see throughout the year, typically with some variations. It might not be mass-mass, it might be mass to volume or volume to mass, but the basic concept we're going to be using again and again and again. Mass-mass, the reason that this is the type of problem that it is in essentially warrants a review video is because converting the mass of one compound to the mass of another compound is not a one-step conversion. In chemistry, we cannot go directly from mass of compound A to mass of compound B. That's not what the chemical numerical ratios are saying. All ratios in chemistry are based on moles. The coefficients in a balanced chemical equation are based on moles. The subscripts in a compound are based on moles, not mass. So when you're dealing with mass, which is a sort of everyday common unit, it's easy to go into a lab and measure out 10 grams of something, you have to convert it. You can't sort of leave it as mass if you're looking at chemical quantities. So you have to take the mass of the first compound, turn it into moles, then use that molar ratio, either the coefficients or the subscripts, and figure out what the other thing is, and then turn moles back into mass. It's a three-step process. First step, you're turning mass into moles. That's using the gram formula mass of the initial compound, the compound that you're starting with. Second step, you're going to turn moles of whatever compound you're starting with into moles of whatever compound you are actually interested in, the one that the problem is asking about. You use coefficients at that point as your unit conversion. And in the final step, because now you'll have moles of the compound that you're interested in, you don't want to leave it as moles, you want mass. So you're going to use gram formula mass of the new compound. It's a different GFM than the one that you started with, and turn the moles back into mass. So mass to moles, moles to moles, moles to mass. It's a three-step process. And we're going to do it all with dimensional analysis, because dimensional analysis, that's what it's useful for doing these multi-step conversions in one go. First problem, we've got a balanced chemical equation. It's supplied to us. It says how many grams of C6H12O6 are needed to produce 2 grams of C2H5OH. It does not matter if you're starting with a reactant and ending with a product, or vice versa. It could even be reactant to reactant or product to product. As long as you have a balanced chemical equation, you're all set. So we're starting here with the number 2 grams of C2H5OH. That's where we're going to start our math, all our math. It's giving us the 2 grams of this thing, and it's asking us how many grams of the C6H12O6 did I need to get the 2 grams of the ethanol. So we're going to start our T-chart here. We're going to start our dimensional analysis here. And as always, first step, mass into moles. So grams of C2H5OH. Grams are fairly meaningless. We need moles of C2H5OH because all of the numbers that are in this balanced chemical equation are based on mole ratios, not mass ratios. So here's where we're using the GFM. GFM of C2H5OH. So you look that up, figure that out, and I would highly recommend you do this as well so that you get the same number that I do. I get 46 grams of ethanol for every 1 mole of ethanol. This is the GFM of C2H5OH. That's step 1. Now we have moles of the ethanol. Now that we have moles, now we are going to use the molar ratio between the ethanol, which is here, and the thing that we're being asked about, which is the glucose, which is here. The molar ratio between the ethanol and the glucose is 2 to 1. That's where the coefficients come in. For every 2 moles of ethanol, 1 mole of glucose was required. This is where we use coefficients. This is the second step, because coefficients are a molar ratio. This gets us to moles of glucose if we were to stop here, but we don't want moles of glucose. It's asking how many grams of glucose we have. So in this last step, we're going to Again, taking that unit, 1 mole of glucose, C6H12O6, and turn it into grams of glucose, 180 grams. This is where we're using the GFM of glucose, a new gram formula mass, not the same gram formula mass as before, because it's all about unit conversion. In the first step, we turned grams of ethanol into moles of ethanol. In the second step, we turned moles of ethanol into moles of glucose using the coefficients. Now we can turn the moles of glucose into grams of glucose using its gram formula mass. That is a 180 at the end, in case you can't read it. And then you are done. At this point, excuse me, at this point, you have converted the units properly. You have the unit that you want, so you can go to your calculator, plug in the numbers from the dimensional analysis, and hopefully we get, and again I would do this too, I would make sure you're getting the same number that I am, 3.91 grams of C6H12O6. You cannot simply look at, take the 2 grams of ethanol and then use the molar ratio. You can't do that because it's a molar ratio, it's not a mass ratio. Second problem, just to go through this process one more time. We've got a balanced chemical equation. Potassium iodide plus lead-2 nitrate goes to lead-2 iodide plus potassium nitrate, and then it's balanced. If 7.63 grams of potassium iodide, that's the Ki, are used, how many grams of lead-2 iodide will be produced? So here's a common question. If you start with a certain amount of reactant, how much product are you expected to get? So we're starting our t-chart, starting our dimensional analysis with the number the problem gives us. That's 7.63 grams, but I'm going to label it as grams of Ki. That's important because as you see, we're turning one compound, information about one compound into information about a different compound. First step, turn grams into moles. This needs to be a gut check reaction for you where you see grams of one thing, think automatically turn it into moles of that thing. So we're going to use the gram formula mass of potassium iodide, which is 166 grams Ki for every 1 mole of Ki. Again, as a reminder, please do take your gram formula masses out to the 10th, not the ones, take it to the 10th. That turns grams of potassium iodide into moles of potassium iodide. Now we can use the coefficients in the balanced equation to turn information about one compound into a second compound. So here, now we're going to look at the ratio. We've got Ki, that's what we have. We want information on the PbI2. This is a 2-to-1 ratio. 2 moles of potassium iodide produces 1 mole of lead-2 iodide. So that's where we're going to pull this in right now. Coefficients stand for moles. 2 moles of Ki produce 1 mole PbI2. Coefficients, molar ratio. Moles of one thing into moles of something else. But the problem isn't asking us how many moles of lead-2 iodide were produced, it's asking us how many grams of lead-2 iodide were produced. So now we're going to take that mole value and we're going to turn it back into grams using the gram formula mass of PbI2, because that's what gram formula mass lets you do. So taking moles of Ki have canceled. Right now we've got moles of PbI2. Gram formula mass says that for every 1 mole of PbI2, it weighs 461 grams. So the final step, we're turning moles of PbI2 into grams of PbI2 using its gram formula mass. You'll see this mass problem. Start with the gram formula mass of the thing that you're given, get moles. Second step, turn moles of the thing that you're given into the moles of the thing it's asking about using the coefficients. Third step, if it's asking for mass, take that moles, turn it back into mass, but of the new thing, a different gram formula mass. When you go through this process, go through this math, plug it into your calculator. Hopefully you get, that's a 10.6 grams of PbI2, 10.6. So 7.63 grams of potassium iodide will produce, theoretically, 10.6 grams of PbI2 if the reaction proceeds as normal. Again, many types, we're going to be seeing this pattern many times this year of taking information about one compound and turning it into information about another compound using the molar ratio in the as the coefficient from the coefficients.